Hi, everybody. Today I'll try to answer a very common question which people have regarding astrophysics, which is that why are planets and stars round in shape? Why are they spherical? And while answering this question, I'll assume that the audience doesn't know vector mathematics, doesn't know calculus, doesn't know Newton's laws of gravitation or even laws of motion. So, without all this mathematical baggage, I'll try to explain why these celestial bodies are round. So, if I don't use these principles of mathematics and these laws of motion, I have to replace all these with some other principle. And I'm going to replace all these physical principles with the principle of closeness. Okay. What do I mean by that? So, it's not very difficult to get convinced that once you have got these bunch of particles as shown here, you've got these bunch of particles which supposedly can coalesce to form a planet or a star. These act upon each other and with the laws of gravity and the laws of friction, right? They are attracted towards each other. So once they act amongst each other with the laws of gravity and friction, let's assume that what these two forces do is that they bring particles together. That's not very unreasonable to assume. So that is my principle. My principle of closeness, so to speak, is that these particles want to get as close to each other as possible. Okay, so we don't work with Newton's laws of gravitation and laws of motion, which are expressed using mathematics of vectors and calculus. Instead, we'll work with the a simpler principle of closeness. These particles want to come closer, and let us see where does this take us. Okay, it'll lead to some very interesting phenomena in the numerical experiments that we will do on our computer. Okay, so as you might have guessed, my approach will not to just tell you things which you're supposed to believe without tweaking things on your own. Instead, we'll do a numerical experiment, the basics of which you'll learn along the way, and you'll see things evolve. And if you want to do these numerical experiments on your computer, you can do that as well. So, to implement my so-called principle of closeness, what I start off with is that I have a bunch of particles randomly initialized in the square, shown by these red circles, and these are supposedly the dust particles which are attracted towards each other with gravity, and there is also friction. Okay, so but in my refined point of view, in my reduced point of view, all they are trying to do is come close to each other. So I have made a computer program, and the algorithm of which uh, says that what it does is that to implement the principle of closeness, what it does is that it chooses a particle at random. Okay, uh, like a lottery, it chooses a particle at random, and then out of these four directions, north, south, east, west, it chooses one of the four directions again randomly, lottery wise, and then it computes if this particle, let's say that it's this particle over here, and it has been the direction that has been chosen is the direction of east, this way. So if it were to move from here to here, would its cumulative distance increase or decrease? Okay, what do I mean by um, cumulative distance? So as the name suggests, the phrase cumulative distance of this particle is basically the sum of the distances of this particle with every other particle. That is the meaning of the cumulative distance of this particle. So it computes if this particle were to be moved in this randomly chosen direction out of these four directions. If it were to be, this has been chosen, this direction has been chosen. If I were to move it, would my cumulative distance increase or decrease? If the answer is that the cumulative distance would decrease, only then the move is made. Okay. If the answer comes out to be that the cumulative distance does not decrease, it rather increases or doesn't change, then the move is not made. And the process then repeats. A new particle is chosen and a new direction is chosen, and so on. So, as you can guess, particles move to make the cumulative distances decrease, and hence bringing these particles closer to each other. So all of this is enforced in this Mathematica code here that I'll just run. Yeah, it's a lengthy code. You don't have to look too closely at it, and you just have to trust me that the code does what it's supposed to do. So if I run the code, these particles start to evolve, and it'll take some time to evolve, but I'll directly take you to the answer. So let's go to the answer. The answer is basically this. It's a disaster. It's not a circle as we were expecting. And if you think about it, the answer is pretty clear. Why do you not get a circle? Well, the reason is that you see in our algorithm, what we were doing is that we were giving preferential treatment to four directions, okay, which were the vertical ones and the horizontal ones. Whereas the real gravity, it doesn't do that. It treats all the directions on equal footing. So because we gave the preferential treatment to vertical and the horizontal directions, what we got was something that was aligned along those preferred directions. And then you might think, okay, how do we fix the problem? The way we can fix it, probably one idea could be that, okay, also introduce the diagonal directions, okay, so as to make it more uniform. But then what will happen is that um, you would be giving preferential treatment to the diagonal directions. Okay, how come? Because if you move, let's say, if you make a movement in the horizontal or the vertical direction by 1 unit, the movement into the diagonal box would be square root of 2 units by Pythagoras theorem. So stepping into the diagonal direction would be longer, would have a longer stride by a factor of square root of 2 as compared to the horizontal and the vertical directions. So basically, if you were to introduce the diagonal directions, the diagonal ones will take the most preference, followed by the vertical and the horizontal ones, and followed by all the other directions which have got zero preference. You never move in the remaining directions. So even introducing the diagonal directions will not fix the problem. All that will give you is a tilted version of the square. Like right now, the square is this way, and if you were to introduce the diagonal directions, you'll get a square which is sort of this way, you know. Um, yeah, because diagonals are basically they can be had by tilting the horizontal or the vertical directions by 45 degrees. That's the connection between diagonals and the vertical horizontal directions. So that is why you get a tilted square if you were to use the diagonal directions. Well, with all this discussion, it's pretty clear what we can do now to get rid of this problem. What we can do is basically get rid of the square grid and let these particles move freely in space. Okay, that is the only way. This is how we can get closer to reality. How the real how the real gravity treats the directions. It doesn't. It has no bias, right, in terms of choosing the directions. Meanwhile, in my animation, as you can see, things have frozen, and again, you have got this, you have obtained this square sort of pattern in your simulation. You don't get a circle. Okay, so now we'll have to implement this refined idea which we have just proposed and see what happens. Okay, so now we have this open grid. There is no square grid restriction. We have this open space over here. Again, the algorithm goes like randomly a particle is chosen by lottery, and then a direction is chosen randomly, and this could be any direction in this plane, okay? Any direction. So using a random number generator, and the move is made if the cumulative distance of this particle decreases. If it doesn't decrease, then the process repeats all over again. You choose a new particle, a new direction, and try to move it. So, and apart from that, I have added some more extra complications in this code so as to speed up the computation and increase convergence. But essentially, the code has exactly what I described to you, apart from some extra complications, which we don't need to go into it right now. You can check the code, the link of which I'll provide in the description of the video. Okay, so we run the code, and as the code is running, you can see the particles they tend to come closer to each other, gather in the center, and this is the trial time, like what trial is it on? This is the trials are numbered. These are called epochs, and it's choosing the particle. Which particle is it working with? Particle number here is displayed over here, and what direction is it working with right now? So, as you can see, this process is very fast. Um, it happens quite fast, and it'll take a while to converge to some final result. But we don't have to wait because I have done this experiment on my own. So we can directly look at the final pattern that might form, and the final pattern looks like so. At epoch number 60,000, it appeared like so. Okay, you move further to 71,000 or even 75. This time it looks like we are getting inching closer to a circle. Okay, so yeah, it works, and it gives us an idea why um, these celestial bodies might give you spheres. But beware that we haven't got uh, a sphere proper, because our simulation is restricted to run only in 2 dimensions, not in three. So you can never get a sphere with this restricted simulation. You have to run the simulation in 3 dimensions, which I invite you to do, because I'm sharing the code with you in the video description. So this is not an argument for uh, the argument for a flat Earth. No, no, no. You get this disk only because our simulation is restricted to happen in a flat plane. If I were to conduct the simulation in 3 dimensions, it would give me a round sphere. Okay, but you're welcome to try it on your own, right? Why believe me? Um, so yeah, it'll take a while for this bunch of particles to make this circular shape, as is shown here. So let me mention that apart from the code that I'm using in this video, these two codes with the square grid and with the open space, they are available in the link given below. But also, if you don't have Mathematica, you can still run Mathematica for free, okay, using your web browser. So the way you do that is again explained in the video description below. So check it out. Now, there is a final takeaway point which I would like to address here, and this is kind of advanced at the research level for for the more expert audience who could be watching this video. So we just observed that if we introduce a preferential directions in my evolution equation or the laws of gravity, then the pattern I get is not a circle. The celestial bodies form patterns other than round spheres. So this means if my laws of gravity, whether it be Newton's laws of gravity or Einstein's theory of gravity or some modified versions of Einstein's theory of gravity, if it had some uh, symmetry breaking, if it had some preferred directions built into it, the celestial bodies that would result, they would carry the signatures in the form of their shapes being aligned in some preferred directions, or they might be rotating or precessing along some preferred directions. So using this very simple simulation, the principle of closeness gives us this hint that maybe we can hunt for this preferential treatment of directions uh, by some advanced speculative theories of gravity, by looking at the behavior of celestial bodies. It could be planets, stars, neutron stars, black holes, and this is indeed one of the methods that people use in modern day research to to look for uh, this kind of preferential behavior in terms of directions in some speculative theories of gravity. So yeah, it's a pretty neat experiment. It helps us understand why our celestial body is round. It's also could be interesting to flat earthers. They can perform this same numerical experiment in 3 dimensions and see what they get. And third, it also gives you some ideas how to work at the bleeding edge of physics research, uh, in terms of like uh, ruling out some of the alternative speculative theories of gravity. Okay, so until next time, I'll see you soon. Bye bye.